What is phase margin and why does it matter for system stability? Imagine you're balancing a pencil on your finger. If you tilt it just a little, it stays upright. But if you tilt too much, it falls. That's similar to what control systems do when they try to keep things stable. Today, we're going to explore a key concept that tells us how close a system is to losing that balance. That concept is called phase margin. In control systems and electrical engineering, phase margin helps us understand how much extra wiggle room a system has before it becomes unstable. It's based on the open-loop transfer function, which is a fancy way of describing how signals move through a system when feedback is involved. The phase margin measures the difference between the current phase angle at the gain crossover point and negative 180 degrees. Think of it like this. When the system's gain reaches a level where the output could start oscillating, the phase at that point is usually around negative 135 degrees. The phase margin is how many degrees you can still add before hitting negative 180 degrees, which is the point where the system becomes unstable. For example, if at the gain crossover the phase is negative 135 degrees, the phase margin is 45 degrees. That means the system can handle an extra 45 degrees of phase lag before it risks oscillating. Why is this important? Because a larger phase margin generally means a more stable system. It can handle disturbances or changes in the environment without starting to oscillate or ring. Systems with a small phase margin are more sensitive. They might oscillate or ring when loads change or components drift. If the phase margin is negative, the system is already unstable and can't handle any additional disturbances. Engineers often use Bode plots to visualize phase margin. These plots show how the gain and phase change with frequency. When the gain crosses 0 decibels, or unity gain, the phase at that point tells us the phase margin. If the phase is close to negative 180 degrees, the margin is small, and the system is on the edge of instability. If it's closer to negative 150 degrees or more, the system is safer. In practical terms, control engineers aim for a phase margin of at least 45 degrees. This gives enough buffer to account for real-world factors like component tolerances, delays, or load variations. Having a good phase margin means the system will respond predictably and stay stable, even if conditions change unexpectedly. In summary, phase margin is a simple but powerful way to measure how close a control system is to oscillating or becoming unstable. It helps engineers design systems that are reliable and robust, ensuring they perform well in everyday situations. By understanding and controlling phase margin, we can keep our electrical systems running smoothly and safely.